Hello everyone, I'm Ashish Darbari, founder and CEO of AXIOMISE. Welcome to my talk. I'm going to be talking about how to use formal verification to vaccinate RISC-V designs against catastrophic bugs. Let's get started. Okay, so our vision for AXIOMISE has been to enable everyone in predictable formal verification. We want all chip designers to enjoy formal, make everyone adept with formal so they can avoid bugs, detect bugs, erase bugs, and prove bug absence so that you can tape out silicon without any bugs. So how are we driving a change? So we're driving a change by doing multiple things. So first of all, we are offering our products. So we are building cool products such as a RISC-V app that I'm going to be talking about. But also we offer extensive modular formal verification training options followed by consulting options to provide hands-on expertise on projects right after the training. And also when you don't have enough engineers to train, I could actually come and help you with services work. We are hiring people in AXIOMISE to carry out this. So this is again an offering to make people more productive with formal. But as I said, the bulk of my presentation today is on the apps side of things, which is RISC-V. So when we're not doing these products, we're actually doing blogs and podcasts. And podcasts in particular have caught up the attention of a number of users and listeners in the world. And if you haven't actually had a chance to listen to our podcasts, I would encourage you to go to Spotify, YouTube, or Apple Podcasts, or even Amazon Alexa or Instagram, and hear us out. And we're having interesting conversations with some of the best-known experts in the field. So we are living in extraordinary times. I think no one can deny this. It is in the psyche for all of us these days. So it makes us all question as to what the hell is going on with the nature these days, and if there is anything we can learn from nature. So I think, yes, we can. And one of the things that I've observed is that the way human body, which is quite a complex machine, how it is able to fight and detect the bugs. So it all starts from the external side first. So our skin, for example, provides the physical barriers. Then you have the tonsils that actually provide you the next level of flagging up, oh, there is a problem in the body, followed by the lymphatic system, the lymph nodes, followed by thymus, going more deep inside where the T cells are actually maturing before they enter the blood and the lymphatic systems, or it could be the bone marrow, or it could be the spleen. So depending on the stage of when the bug has been caught by the human body, different actions are initiated by different monitors inside the body. And I think this is fascinating that although the human body seems quite simplistic from outside, there's a lot going on inside in order to actually tackle the onset of bugs and infections. And then, of course, the all too familiar immune system kicks in and tries to protect us. So this has an interesting parallel with silicon, with chips. And in the way that actually, especially if you're using formal verification, then we actually end up writing lots of different checks to check the health of the chip in different scenarios. So let me explain what I'm trying to say. So if you're going from architecture to silicon, you're bound to have lots of numerous verification challenges at each stage, whether it is the instruction set architecture correctness at the architecture level, whether we have the right ISA in place in terms of consistency, whether we are handling coherency, multi-threading, or it could be security, safety, power. And these things could run all the way down to silicon. So this could actually keep you occupied in terms of verification concerns if you go from architecture to silicon. If you go deep into the microarchitecture layer, you are talking about verifying arbitration, serialization, clocks and resets, deadlocks. And at the netlist level, most of us focus on synthesis correctness, clocks and resets. But actually, if you look at it, there are different verification concerns, just like the human body is coping with different kinds of verification, bugs and whatnot. At the chip level, we are actually facing a plethora of all of these concerns. So we could be fighting for, bugs that manifest as deadlocks or as X-propagation bugs or lockstep verification or low power or security. And it's a big mishmash, the figure that I can think of that expresses this most aptly is that it really is a concoction of all of these concerns. But you know what? The good news is that if we do verification properly, especially employing formal methods, we could actually attack all of these verification concerns in very much the same way as the human body does. Of course, we don't have an immune system in the chip. We're not talking about error correcting chips yet. We could verify them, but in general, chips don't autocorrect themselves and offer an immunity just as the human body does. It does in some cases, but it's not the norm anyways. Right, so what happens when we get it wrong? So we're all too familiar with the Intel FDIV story from 1994, when Intel recalled all the defective processors, and they had to pay a big sum of money. It was, in the press. So it's not something that is new, but I just thought I'll flag it up again to remind people of what can happen when things do go wrong. Ariane 5, again, a well-known story documented. When the European Space Agency launched this Ariane 5 in 1996, it exploded soon after the launch due to an error in the inertial reference system, due to a 64-bit floating point number being assigned to a 16-bit signed integer. And Meltdown Inspector, everybody knows, has been in the news, and all of its related bugs and security vulnerabilities that have been known to us since then. It's everywhere. Side channel attacks or non-side channel attack issues. Security verification is a hardware problem too. So whether it is reliability or liability, whether it is requirements that you have to enforce when you're building things, for example, adherence to DO254, ISO 26262, or emerging security standards, the requirements for verification are now becoming increasingly more complex. And one has to make sure that not only does the reliability need to be in place, the liability needs to be in place as well. But why is processor verification hard? So coming back to our RISC-V processors verification story, because it's not just functional verification. Cores are complex, massively optimized. You've got pipelining, interlocking, forwarding. You've got branches, jumps, exceptions, stalls, interrupts, debug, extensions, clock gating, arithmetic, power, safety, security. The thing is, all of these optimizations are crisscrossing with each other in terms of what they're trying to do. And with hundreds and thousands of instructions in flight and different interleavings and different dependencies and hazards, how do we know that actually we haven't made a mistake? Miroslav Velev carried out a number of student projects and published a paper in ITC 2003 and documented in detail what happens when you actually build complex processors of different types. And he documented a whole range of bugs that actually not only do students, make mistakes, but also professionals in industry make the same mistakes. I have personally verified processors with similar kind of bugs in them, having been pre-verified before, for example. So it's not like these things are absolutely trivial. So simulation, which is the state of the art in verification and is used most widely, is dependent heavily on stimulus. And that, my friends, is also the reason why it is not adequate. Too many dependencies and scenarios to cover exhaustively. Now, traditionally, conventional verification of microprocessors relied heavily on architectural testing, interleaved instruction sequences. Do they always work as expected? Okay. The architect would send different instructions or different combinations of them. But one can only do these finitely many times. You know why? Because even for a small core, we're talking about 32 registers. So if there's 60 plus user instructions, a wide number of permutations. How about verifying that certain optimizations such as data forwarding do not break the functionality? And consider verifying all the permutations, not just of OR, XOR, AND, but all of these instructions and all of the permutations, different registers being shared. So this is not a humanly feasible task, my friends. So what is formal verification? So I'm a big fan of formal. We build products using formal verification under the hood. It is mathematics and automation. It's a rule-driven verification paradigm. Earliest origins is in theorem proving, which doesn't have the problem of state space exploration issue that model checking has and equivalence checking have. But theorem proving, the problem is there's a big steep learning curve, and there are no counterexamples that are produced automatically. Whereas with model checking and equivalence checking, one gets waveforms as counterexamples so you can see what's going wrong. The most famous example of model checking is property checking, which is how many of us know this in today's time. Right, so just trying to give you a brief comparison point of simulation versus formal. So UVM, as we all know this fondly, is heavily randomized in presence of constraints. Whereas formal verification, on the other hand, is actually relies on systematic state space exploration. So starting from reset, the tools expand the state space search, and as we go along, they try and find if there is a state in the exploration which violates the property. So that's the key difference between the two paradigms. And how are checks written in formal? They're written using properties which have precise mathematical semantics. So for example, if I was writing a check to check if the branch if equal to instruction works correctly, I would say, well, assert property. If a branch if equal to is issued and the register values RS1 and RS2 are equal, then register delay cycles later, some delay cycles later, depending on the microarchitecture of the design, the next state of the program counter is going to be the same as branch address. And we can go and look at the RISC-V ISA, look at how the branch address is meant to be computed, what does a branch opcode looks like, and we can code this, put this property in the formal tool, and the tool will explore all possible combinations of other instructions with BEQ. And if it cannot break this property, it will come up with a proof that BEQ works for that processor. Property itself is quite succinct, as you can see, compared to some of the test bench cases that you would write. It's quite precise and has a mathematical meaning. And the whole formal verification task is actually driven by requirements. So what are the challenges with property verification? Property checking based verification has problems of learning curve. So we are obviously noticing this, and this has also been a challenge in formal verification adoption, that there is a learning curve and a lot of the people are actually scared of learning it. Now we at AXIOMISE are training lots of engineers, but of course it takes time to build that experience. So writing efficient properties for performance takes experience. Proof convergence in formal verification is challenging, and coverage is not homogeneous across formal tools. So this also prevents a barrier to people who are moving to formal but are struggling to homogenize. So this is one area where we have actually plugged the hole in our solution. So our solution is called Formalizer. Formalizer Ultra because it includes the new coverage solution. With our solution, you can now visualize instruction set architecture, you can obtain coverage analysis, you can build proofs of bug absence, you can find bugs, all without having to write a single test case. No test cases to write, no manual checker to write, no verification code to be written. Exhaustively prove that all ISA instructions work as expected under all conditions. What goes in our app? Your RISC-V core setup file that maps the architectural states with the microarchitectural signals in your design, and a coverage specification if you're interested in this coverage analysis. What comes out is exhaustive proofs that mathematically prove under all conditions that each instruction in the ISA works always as expected. Scenarios as specified in the coverage specification can always happen. Visualize that scenarios in the coverage specification can happen. So we are offering both of these facets with our coverage analysis. How does it work? So we have taken the RISC-V ISA, we've distilled it down into a set of formal properties in our formalizer. Then you bring along an RTL file, which is your RISC-V core, and a setup file, both of which can change as the design evolves. But assuming they've both stabilized, you basically then feed in the properties into a formal tool, and the tool, such as the one from Cadence Mentor Synopsys, would produce a fail or a pass. We are vendor neutral. Use any formal verification tool you like. You can get failures, you can get proofs of bug absence. Isn't that awesome? Now, this is a dashboard coming out from, I think, Mentor's Questaprop check. And this is a case study from IBEX. 50% of the proof results were ready in less than 30 minutes. We were able to exhaustively prove that the processor worked correctly under the conditions that we verified this in. 80% of the proof results in 2 hours. Isn't that cool? We are exhaustively able to prove it. Now, when the processors become more complex, for example, CV32E40P that we've been looking at, the proof times increase. For example, in the case of verifying store byte instructions, some of the proof times were in the region of 10 hours, 40 minutes. But yet, we know exhaustively that any combination of stored instruction in flight is now verified. So how do we test the quality of our checks? Why should you believe it? So what we do in our exercises internally is we keep breaking the designs to test if the checkers actually work. So this is an example of the BEQ check that I showed you earlier. And what we're saying here is that the BEQ instruction, when it gets issued 2 cycles later, the next state of the PC must be the branch address, which is this value. So this is the desired behavior. I've written a cover property, ran it in Cadence's Jasper Gold, and I've got a passing cover. So does it mean that my BEQ instruction always works correctly just because I've been able to prove a cover point? No. As it turns out that actually with this bug insertion, the properties that check BEQ failed. Not only that, we have an invariant on the program counter which maintains what are the legal states of the program counter that also failed. And they both failed quite quickly in 20 clock cycles. So we are able to catch a number of these bugs, and that's how we're able to assure to our customers and to ourselves that we are actually doing a great job at checking these things. But what are the challenges with formal verification, and should you trust it? Well, we've actually done the due diligence of making sure that the specifications have been mapped to the properties properly. We review pass and fails, reviewed constraints, review the structural coverage, the functional coverage metrics, and hand-based mutation. Most of these good tools actually provide with hooks and push button commands to get this data. But friends, is this enough? How do we know that all instruction sequence interleavings have been verified? Just because I tell you that I have a proof that a BEQ works correctly, how do you know that there were instructions that were sent earlier than BEQ? And how do you know the BEQ instruction was followed over by another instruction before the effects of BEQ were committed? People say, show me that you've tested all sequences. Prove to us that you've tested all sequences. So to address some of these concerns, we've actually built a brand new ISA coverage analyzer. We have the checkers and the cover properties from our proof kit last year, which were derived from ISA, which were set up by human beings against an RTL core, went in the tool. Now we are actually taking a coverage specification, and that goes in our coverage analyzer, and we're able to show you example cover properties, waveforms, or unreachable scenarios, and reports. And you know what? The best thing is that all of these coverage reports and the coverage database that gets built is interoperable between different formal tools and across simulators. So there's no vendor lock-in at all. Right, so I'm going to now show you how to use Formalizer in an agile way. So 9th July CV32 gets checked up, the setup was made, then we went and pressed these buttons, prove and cover, and we got our nice little dashboard. 16th of July, we repeated the same flow. We may have a new setup file because the design may have changed. We may not have a different setup file, but we again pressed the prove and cover buttons and we got the new dashboard. We had to do nothing more than that. We can find bugs, we can have proofs of bug absence, and interoperable coverage model. So friends, this can be used by architects to ensure that multiple instruction implementations work and don't introduce new bugs. It could be used to visualize what is and isn't possible. Designers who need to know that they have not introduced new bugs could use it. Visualize ISA scenarios using our app. You know what? Don't have to write any test cases. Just press these buttons in the app. The verification engineer could use this in the continuous verification mode like I was showing you on different dates for 9th and 16th July. As design fixes are applied and design transformation happens, we can continue to prove correctness, obtain formal guarantees from assertion checks, and get coverage metrics from ISA Coverage Analyzer. We can actually do end-to-end architectural verification, obtaining structural coverage information from formal tools, and sign off against the ISA Coverage Analyzer output. This is, my friend, the strongest form of sign-off you can get. Building proofs of bug absence, establishing coverage reports that are interoperable across simulators and formal tools. And guess what? You don't even have to write a single test case yourself, right? You can bring in any graduate into your team and they can run their Formalizer app for you, and designers and architects can start to fix the issues. Or managers can say, hey, cool, everything is working all right, we have proofs, we can move on. Let me show you an example of a coverage analyzer. So this is the data forwarding case. What we're saying here is we're going to establish conclusively that the OR instruction works correctly regardless of any instruction interleavings that we already used to do last year in our proof kit. Now we are saying the coverage specification says, what if the OR instruction was preceded by a well-defined instruction called subtract, which had 2 repetitions of it 4 cycles after the reset was detected, and after OR was issued, 1 occurrence of AND was issued 1 cycle later before the OR was committed. Can OR work correctly under this restricted directed sequence? And is it always the case that if we send this sequence, OR will always work correctly? So we are able to establish that OR works correctly regardless of these interleavings. We are able to prove that OR works correctly with respect to this specified interleaving. And we can also show you why this actually happens by producing to you a nice coverage report in the form of a waveform. And as I said, this is a data forwarding case. We are able to see that registers are shared between these 3 instructions, and the subtraction instruction was issued 4 cycles after the reset was detected. So we do a lot of different kinds of analysis in the backend for every specification that you give to us in the Formalizer app. It all happens automatically. These are the proofs that you were getting last year. The fact that we were able to prove that the OR instruction was working correctly regardless of the instruction interleavings and the associated cover property. But now we are able to prove all of these extra scenarios that you have asked us to prove by way of giving us a coverage spec. So by virtue of putting it in the app, we are able to automatically synthesize the properties and test whether or not these things work always and can they work. And do we find bugs or what? So we found tons of bugs in ZERORISCY, micro-risky, pre-verified before, and IBEX, and we did all of this work, and we proved exhaustively the design conforms to the RB32 IC subset of ISA. We were able to establish why it was the case that there were bugs. For example, we showed that the ZERORISCY had an architectural violation for the load instruction because of a custom reg load interfering with it. We also found that if a debug request came in the middle of a decode, IBEX would malfunction for all of the instructions. This was a real corner case. It was caught in 7 cycles. And you know what? It was so easy to do this. Just literally press the buttons in the app and off you go. Why does our solution work? Because Formal gives us a natural ability to explore designs for deeper bugs and proofs. Our property base is designed by hand to be efficient, and we exploit a range of techniques based on our experience with Formal, abstraction being one. And we don't do just one, but many different abstractions, for example. So key features of our Formalize app is this push button, GUI based, can find efficiently bugs without writing any test cases, exhaustively prove compliance of ISA, visualize ISA behaviors as you develop new instructions without writing any tests, prove and visualize as you build adopting an agile design verification flow, has predictable runtimes, and expose security trojans. And you know what? Use ISA coverage analyzer for sign-off. So in summary, bugs are a natural consequence of design. Bugs caught late in the design cycle result in very expensive fixes and catastrophic failures. Formal enables efficient bug hunting right at the time of design bring-up. Architectural validation must employ formal verification to build proofs of bug absence. Architects, designers, verification engineers can all use Formalizer without any FV experience to find bugs, build proofs, and obtain interoperable coverage model for use in simulation and other formal tools. Use any formal verification tool of your choice, but let us vaccinate our chip designs using formal verification. And now, my friends, I'm happy to take questions. If you do have more questions that I can take today, please reach me out to ashish.darbari@axiomise.com or info@axiomise.com. And I'm all yours now. Thank you very much.